this introduction. So today I will present you a different version of total flow analysis and show you that all these versions are equivalent. So total flow analysis is a method that performs worst case analysis, for example, for time sensitive network. And the goal is to obtain deterministic bounds on worst case delay, delay jitter, and backlog. There exist different algorithms that use total flow analysis. And it depends on the graph induced by flow path. So I will come back later on what is the graph induced by flow path. And if this graph induced by flow path has no cyclic dependency, so there is TFA himself, which was introduced by Cruz in 1991. And there is also improvements such as TFA++ that take into account the shaping effect by Mivdawi and Ledier in 2017. When the graph induced by flow path has cyclic dependency, the problem is more challenging because we don't know if there exist deterministic bonds or not. And Thomas et al. Introduced an algorithm fixed point total flow analysis. So I will explain also this algorithm in detail in further slides. But one of the ideas is to cut the network and then do a TFA analysis on the cut network. So the first question we ask is, does this show at an influence on the result? If we choose a cut or another cut, does it has a different result in terms of convergence and in terms of bounds we obtain? The second point is we notice that there is a drawback in this algorithm is the time computation of cutting the network, because they want a minimal number of cuts, and so they perform this thing. And the question is, can we avoid cuts? And that's why I will present you a different algorithm, several algorithms that solve this problem without cutting the network. So before presenting all this algorithm, I will introduce the system model. So we consider a packet switch network. Each device in the network contains an input port, a switch fabric, and an output port. And inside each input port, we have a packetizer that releases the data when the entire packet is received. Then it is transmitted to the switch fabric, and then to one of the output ports of the device, which is composed of a scheduler. Each scheduler separates the traffic by class, and in each class, we assume that there is a FIFO policy, first in, first out. Each scheduler is, as we assume that they have a minimum service curve, which is rate latency. And for the flow model, they are unicast or multiclass, and we assume that they have a fixed path, and the traffic at the source is constrained by a leaky bucket arrival curve, where rate R and burstiness B. So here, if we want to compute a worst case bound on the delay, so it corresponds the delay computation for one. It corresponds to the maximal deviation between the arrival curve in yellow and the service curve in red. So here it's for one server on one flow, but networks are more complicated because there is several flows on server. So I will show you different algorithms. So total flow analysis to begin. I will apply it on a simple toy network, which is composed of five devices. Each bracket represents a port, and we label the output port by a number of 6 or 7 or 8 or 9 or 10. And we define the graph induced by flow, which is a directed graph whose vertices are output port. So here vertices is 06. And there exists an edge if at least one flow crosses a link. So here for link 06 or 07, we have 3 flows for red, blue, and green that crosses this link. And we want to apply total flow analysis on this network. So let's focus on the two first output ports. So total flow analysis will first compute the delay. We have the delay function, which depends on the input burstiness for each burstiness for each flow. And there is some TFA++ and FP TFA takes into account the shipping effect on the packetizer to compute the delay. And then when we have computed the delay at the node, which is the maximal deviation between the aggregate flow and the service curve of the server, we compute the output burst for each flow, which is the input burst of the flow plus the rate of the input part of the flow at this port, plus the rate of the flow times the delay at this port. And we do this step 1 and 2 for each server in the sense of the flow until reaching the end of the network. So 06, 07, 08, 09, 10. And at the end, we obtain the worst case analysis. So this is done for a network without cyclic dependency. But when we have cyclic dependency, it is more complicated, more challenging. So I will use during all the presentation a toy network that has the cyclic dependency. We have 2 cycles on this network. Why we have a cycle? It is because, for example, at node O6, we have 3 flows that compete to exit the node O6. So the output burstiness for the flow is increases and is then transmitted along the path of the flow, all flow, until reaching the node O6. So at node O6, the input burstiness depends on the delay at node O6, which himself depends on the input burstiness. So we have a cyclic dependency. One solution, so TFL doesn't work on this algorithm, on this network, because they are cyclic dependency. And one solution which was proposed by Thomas et al. Is to cut the cyclic dependency. So here we have 2 cycles. So there are 3 different ways to cut the network and 3 ways to apply FPTFA. So the question we ask is there a best version between the three cases? And do they provide same output burst? And do they have the same convergence criteria? So before showing that all these versions are equivalent, I will show you FPTFA. So how works the FPTFA? So I take a specific cut here to apply FPTFA. So I cut link 01, 06, and 010, 05. And then the step 2 of the algorithm is to label the node, such that when we follow a flow, the label must increase. So let's take this. This is one of these labels, but there are several different labeling. So here, for example, we follow the green flow and the label increases. The same thing if we follow the brown flow. And here the node 08 depends on node 011 and 07. So the label must be higher than 011 and 07. So we continue to label all the network until reaching the end of the cut network, which is non-cyclic. And then we perform a TFA analysis node after node in the order of the label on the cut network. So what we have an input burstiness at the cut, ZL. Then we have a function FL, which perform a TFA update of the burstiness and the delay. And at the output of the network, we have an output burstiness vector of burstiness. And FPTFA iterates this function, this specific function FL, until finding a fixed point or diverging, because we don't know if there is a result. So yes, so we find an algorithm that find a fixed point. So this is good, but does it provide valid DD bound for the network? So Thomas et al. Provides a proof. But we build another proof, which is alternative and will be useful for the rest of the presentation to prove that the others algorithm are valid also. So to do that, we use a time stopping method. So let us assume that we stop all source sending at time tau, and the worst case burstiness between 0 and tau satisfies this inequality due to the function FL. So worst case burstiness at tau is less than equal FL of the worst case burstiness at tau. And we define this set, which is very important for the rest of the presentation also, which is low de FL. This is all the Z, such that Z is less than equal to FL de Z. And we see that this worst case burstiness at tau belongs to this set, low de FL. And as it is valid whatever the tau we consider, we see that worst case burstiness belongs to this set, low de FL, whatever the tau we consider. So the problem is now reduced to find an upper bound on this specific set, low de FL. when we see that, we think about the Knaster-Starsky theorem that says that that says that the least upper bound on load Epfl is a fixed point of Epfl. But I will show you that this theorem is not helpful in our specific case. Indeed, if we consider these two functions, the function f1 and function f2, and we extended it to infinity, we see that the Knaster-Starsky theorem gives us the same value, which is plus infinity. So that's why we build a theorem that says that this is not the good. Okay. That says that either sorry. So our theorem says that if load Epfl is bounded, so don't take a look on that. It's not the good slide. If load Epfl is bounded, then there exists a solution of our problem, and this solution is a fixed point. Is a fixed point, and this is the largest solution of load Epfl. So let's come back to our problem. Here, with this theorem we have introduced in our paper, we see that it exists. We see that it exists an upper bound on load Epfl if there is a we see that there exists a lower bound on load Epfl. Moreover, we introduce another theorem which says that if we have some property on the Epfl function, it means that if Epfl is concave and strictly positive in 0, then it means that we show that this fixed point that we have found is unique. This is and give us a unique valid delay bound. So this proof will be will be used also for the next slide. So we see that FPTFI uses cut, and give us a valid delay bound. And now we will introduce a new class of algorithm that does not use cut. So we introduce this algorithm, which is called synchronous TFA. So sync TFA, what is the goal of sync TFA? To simultaneously update D for all node and Z for all transition edge. So D is the delay jitter bound vector, and Z is the burstiness bound vector. And until finding the fixed point or diverging. So what is the difference with before? So for node I we compute in the same manner. So di is equal to the delay which depends on the input burstiness at node 06. But for the output burstiness computation is a bit different, because instead of taking into account the input burstiness, we take into account the input burstiness of flow in the network plus the rate of the flow, as we can see here, times the accumulated delay jitter along the path of the flow. So here it's from 01 to 06, and we compute the delay as it is. So the advantage is there is no cut way. So here we see we can introduce, as before, the same set load G, which is the set of ZD, such that ZD is below or equal to J de ZD, and we can build a scheme of a fixed point scheme. So we have here a dz vector, and then we apply the J function, and we obtain a d prime and z prime d prime and z prime vector. And then we solve the fixed point solution. And as FPTFA, as the J function is concave and G of 0 is strictly positive, if we have a fixed point to this solution, then this is a unique valid delay bound. So I have shown you two algorithms, FPTFA and sync TFA. They have both a unique valid delay bound, which is fine with the iteration scheme. And we introduce in your paper a new theorem that says that these two algorithms are equivalent. If one converge, both converge. If one diverge, both diverge, and they obtain the same output bounds. So the one key point of the proof is to do a mapping between the G function and the Epfl function. So what it shows that it shows another thing. It shows that whatever the choice of the cut we do on FPTFA, it is equivalent to CTFA. We have the same convergence, whatever the cut we consider. So FPTFA algorithm finds the same bounds, the same unique bounds, whatever the cut we consider. Now we see that the CTFA is a sequential way to, we do a sequential update for CTFA at each loop. And we see that to compute the next delay and the next burstiness, at each time we use the whole value of D and the whole value of Z. So what we propose is an improvement of CTFA, which was used to build this equivalence between CTFA and AltFA. And we introduce an asynchronous algorithm that uses the new value of Z and the new value of D at each time. So it updates immediately the vector Z and vector D. And moreover, we can compute and update only a part of the network at each iteration. So an algorithm is perhaps better than a slide with wrote. So here we see this asynchronous TFA algorithm. So we see that the par4 loop at line 4 do a TFA update for the subset of nodes. So here I choose the subset of node O1, O3, and O5. And then I compute the delay and the burstiness in two parallel sections. So this is a parallelized algorithm and non-deterministic. And so what we see is that we use at each time here the most recent value of D and Z, which are used. Of course, we need to as we see just a part of the network, we need to visit all nodes enough time to ensure that we will have a convergence if the convergence exists. We prove also that there is the equivalence as before, but this time with async TFA. So we extend this theorem. So we find that async TFA, sin TFA, and FPTFA find all the same bounds and all the same results of convergence. And so this is one of the points of the. And now I will focus on a special case, which is alternative TFA, AltFA. So in that case, all nodes are visited simultaneously at every node. On each parallel section, section 1 and section 2 in a previous algorithm is done sequentially, but inside each section, it is done in parallel. And we obtain this algorithm, which use here the most recent value of the delay jitter bound to update the Z value. We apply that on a simple example to show some simulation. And we apply that on a ring network of n nodes. And each flow crosses n-1 different server. We see that each flow begins from one server, cross all the nodes, and go outside at the n-1 server. And we show the rate latency, latency for the server of 1 millisecond on the rate of 10 to the power 7 bits by second. And the rate of the flow and the burstiness of the flow are such that. So we have an utility on the 70%. We do AltFA and we compare it with FPTFA. As we have anticipated with the theorem, we obtain the same end-to-end delay bound. But we see that AltFA converge faster than FPTFA. And this thing should be waiting also because as we use at each time the most recent value of D and Z, we should have a quicker convergence. And here in this example of a ring network for 25 nodes, we see that our algorithm goes 3.8 faster than FPTFA. So to conclude, we see that the choice of cut in FPTFA has no influence on the output result of the convergence. So they have all this, whatever the cut we consider, they have all the same results. So we see also that we can introduce new algorithms that don't need a cut to compute delay bound in cyclic network. we have introduced two new algorithms, sync TFA and async TFA. The advantage of async TFA is that it could be faster in terms of resolution. And then we prove in our papers that FPTFA, sync TFA, and async TFA obtain the same result. They have the same condition of convergence. If one converge, both the three converge, and if one diverge, the three diverge, and they have the same output both. So this is the references. I thank you for your attention. I will be happy to answer all your questions.
So, questions? I have a few ones, but I will take up a little slide. I have one on slide 21. Here, the game, which is like huge, does it need for LTFA the parallel?
I use
sorry, could you repeat the question for?
Yes. Did I use here for LTFA the parallel version? Yes, I use the async. The LTFA is done with the parallel version, so I parallelize for all nodes, and this is done with parallelization. Yes. Yes, yes. Different course, and I do it in parallel.
And the time here, for LTFA does not include the time to select cut because you have like that one. So the time that you show for LTFA is only the computation.
Yes, there is no the cut. Is this graph represent in this picture? Do we take into consideration the time to cut the network? No, this is true. It will be an additional time. So this is the difference is higher. So here it just we consider because as it is a ring, there is only one cut, and so I did it before, and I just take the time computation to apply LTFA on TFA on that example. So you are right. Yes, the difference should be higher.
If you start from a point that is not a lower bound of the fixed point, do you have also some convergence results?
Can you repeat your question?
Here you start from a point that is zero everywhere, and then you iterate to get convergence to the fixed point.
Mm-hmm.
Now, if you start from another point, so you have a convergence from the bottom.
Mm-hmm.
And what if you start from another point, maybe an upper bound of the delay?
Yes. Yes. If I start the fixed point resolution from another point instead of zero, do I obtain different bounds? This is yes. So the question here is not asked because we find a maximal element to load the Epfl. As I can come back to this slide, even if yes. We find the maximal element of load Epfl. So after this is the resolution problem is to find the fixed point, but this is another question. So yes, you can have different fixed point, but the theorem remains the same, even if you take another way to find the fixed point.
But you did not answer. You just said the answer. The question is not asked, but the question is asked. Right? What happens if you start with an initial condition that is not zero? Do you know? You could do that, right? You could start with whatever.
Yes, we can.
Discuss after.
I think that the result is that we should start from zero, from the lower bound. Then it's guaranteed to converge to the largest element if it is bounded.
If we start from another one, I think we.
It's possible, but it works also. It's not just.
have a last question. No, we have a lot of questions after that. Okay, so to be on time, to thank the speaker and